sets, miscellaneous exercise in chapter 1. We'll see what is question 1. Decide among the following sets which sets are subsets of one and another. A is equal to x such that x belongs to R and x satisfy x square minus 8x plus 12 equal to 0. B is equal to 246. C is equal to 2468. D is equal to 6. So what's given to us? It's given that the x belongs to R which satisfy this equation, that is x square minus 8x plus 12 equal to 0. We'll find out what are the factors of that. So we can see here that we have x such that x belongs to R and x satisfy x square minus 8x plus 12 equal to 0. So factorizing it, what are the factors of this? Minus 8x can be written as minus 6x minus 2x, and minus 6 into minus 2 will give you plus 12. So here you are getting factors as x into x minus 6 minus 2 into x minus 6 is equal to 0, which implies that x minus 2 into x minus 6 is equal to 0. So therefore A consists of two elements, that is 2 comma 6. Now B is having 246, C is having 2468 and so on, and D is equal to 6. So we can see here that every set which is over here is nothing but, here it is a subset. A is a subset of C, B is also a subset of C, and D is also a subset of C. You can see that all the elements are there in C. Now A is the subset of C and A is the subset of B also. Here I have written that. And then we also can see that B is the subset of C only, D is the subset of A, D is the subset of B, D is the subset of C. So hence this he is asking the question, which are the subsets, what are all the possible subsets which are subsets of one and another, he told, right? So therefore this is the way we write it. Next question. In each of the following, determine whether the statement is true or false. If it is true, prove it. If it is false, give an example. So over here you are having the first one. If x belongs to A and A belongs to B, then x belongs to B. Here small x is nothing but an element of A and A is nothing but a subset of B. So here we have to take such that the first one is false. Why is it false? We'll see. Because it's given that x belongs to A and A belongs to B, then x belongs to B. It doesn't mean that this element can belong to B. So we'll just see why it is happening. So false. Let us suppose that A is equal to 1 comma 2 and B is equal to 1 comma 2 comma 3 as a set with braces there. So we have here 2 belongs to the set 1 comma 2, that is 2 belongs to set A, and 1 2 is an element which belongs to set B, that is 1 2 belongs to 1 comma 2 comma 3. In braces we are writing this. So we can see here that very clearly that this is all not written in here. This element, it is an element of B. So this element definitely will belong to B. So therefore A belongs to B. Here you are having A belongs to B, but 2 in separate, nowhere in the set you are having 2 separately written. But if 2 does not belong to the set B, isn't it? So therefore the first solution, first statement is wrong. Now going into the second one, if A is the subset of B and B belongs to C, then A belongs to C. So now this is also false. Why? We'll see. So let us suppose that A is equal to 2 and B is equal to 0 comma 2 and C is equal to 1 comma 0 comma 2 comma 4. So therefore here you are having A is the subset of B. We can definitely see that 2 is there, therefore this is the subset of B. Whenever you are writing all the elements of B, what will you write? You will write it as, because this is only one element, it is there in B and A, therefore A is the subset of B and B belongs to C. What does this B belongs to C means here? You can see that 0 2 is an element of C. So therefore that's why we'll tell elements belongs to C. That means 0 2 belongs to C. B means here B is nothing but it is equal to 0 comma 2. So therefore here B belongs to C, but A does not belong to C. This 2 is not an element of C. It is not in this. It is not written separately in this braces over here. So therefore A does not belong to C. That's why it is a false statement. Here, next, here we had, actually it's given A belongs to C, but we have seen that A does not belong to C. Now third one, if A is the subset of B and B is the subset of C, then A is the subset of C. So we'll see here how it is. See, because true, this is very much true, because now A is the subset of B. So which set is bigger? B is bigger, isn't it? And B is the subset of C. Now which is bigger among all the three? A, B, C? C is bigger, isn't it? So let us suppose that X belongs to A. Then X will also belong to B, and it will also belong to C. So therefore A is the subset of C. You can see that which is bigger. Because this is the subset, this is bigger. This is the subset, this is bigger. And because A, in all the three, C is the bigger one. Therefore definitely A will be the subset of C. So this statement is true. Next, fourth one. If A does not belong to B and B is the subset of C, then A is not the subset of C. So we'll see what is the fourth statement. This is also false. So we have to take one example and do. Here it is why we have to see that A is not the subset of B. Also B is not the subset of C. Let us assume that A is equal to 0, 1, B is equal to 0, 3, 4 and C is equal to 0, 1, 2, 6, 8. Now since 0, 1 is not there in B, therefore A is not the subset of B. And since here B 0, 3, 4 is not there in C, therefore B is not the subset of C. But here it is, we have that A is the subset of C because 0, 1 is there in C. So therefore A is subset of C. But here he is telling that A is not a subset of C. We have proved that A is the subset. A is the subset of C is the correct statement, true. But if A is not the subset of C, it is a false statement. Next, fifth one. If X belongs to A and A is not the subset of B, then X belongs to B. So now here this is we are going in fifth one. So fifth one, it's also a false statement. We'll see why. From the question we have X belongs to A, also A is not the subset of B. So let us suppose that A is equal to 1, 2, 3 and B is equal to 1, 5, 6. Definitely we can see that A is not a subset of B and 3 does not belong to B. Isn't it? 3 does not belong to B. But here it's given that 3 belongs to B. So therefore here this is a false statement. We proved that it does not belong to B. Now next, sixth one. If A is a subset of B and X does not belong to B, then X also does not belong to A. So is this a true statement or false statement? We'll see. It's a true statement. From the question we have that A is a subset of B and X does not belong to B. So let us assume that X will belong to A and X will belong to B. From the question we have that X does not belong to B. So if A is the subset of B, so therefore X also does not belong to A because A is the subset of B. It should be smaller, but all the elements of A will be there in B. If X is not there in B, definitely it will not be there in A because A is a subset of B. Hence it's a true statement. Let A, B and C be the set such that A union B is equal to A union C and A intersection B is equal to A intersection C. Show that B is equal to C. So now what is given in this? We are having A, B and C are sets such that A union B is equal to A union C and A union B is intersection B is equal to A intersection C. So to prove that B is equal to C, so let us suppose that X belongs to B. We are taking some element X belongs to B, which implies that X will definitely belong to A union of B because what all elements are there in A will also be in B. Since here B is always the subset of A union B and A will also be the subset of A union B always. So therefore which implies that X belongs to A union C because A union B is equal to A union C. So therefore X will belong to A union C. Since A union B is equal to A union C, which is given to us, we have that X belongs to A or X belongs to C. So now we are having first case here X belongs to A. If X belongs to A, what will happen? X belongs to A and X belongs to B also. Since we started with X belongs to B, implies that X belongs to A intersection B, which implies that X belongs to A intersection C since A intersection B is equal to A intersection C is given. So therefore we have x belongs to A and x belongs to C, therefore which implies that x belongs to C also. So now since x belongs to C, we have therefore x belongs to B, which implies that x belongs to C also, since we started with x belongs to B, right? Since we having from here x belongs to C, and we have seen in the since x belongs to B also, it implies that x belongs to C, since we started with x belongs to B. So B is definitely the subset of C. So this is the first one. And next, similarly, we can see that C is the subset of B. From second, if we take that as second, so from 1 and 2 we have that B is equal to C. Both are equal because we have proved that same element is in there in B. It's also there in C. It's also there in A. It's also there in C. So we can see that A intersection B is equal to A intersection C, and A union B is equal to A union C. Because of that property, we can prove that A intersection C is equal, B is the subset of C and C is also subset of B. Therefore, B is equal to C. Next, going into question 4. Show that the following 4 conditions are equivalent. Now, following 4 conditions are equivalent. What do we do is, we'll take the first one and prove that it is equivalent to the other 3. You can take the second also and prove it is equal to 1, 3, 4. Or you can take the third one and prove that it's equal to 1 to 4, or fourth one you can take and prove it is equal to 1 to 3. So now I'm doing here, taking the first one and I'm proving that it's equal to the other 3. So let us consider your first one. A is the subset of B. So now we have to prove that A minus B is equal to 5. That means empty set. So here, if possible, let A minus B not equal to empty we are taking. So let x belongs to A minus B. So which implies that x belongs to A and x does not belong to B, isn't it? So which implies that if x belongs to B and x does not belong to B, we having 2 statements which we got here, right? So there, since A is a subset of B, so therefore definitely if it belongs to A, it should definitely belong to B. So therefore here, is this case possible? So therefore our supposition is wrong. We cannot take that x does not belong to B. So therefore our supposition is wrong. Hence A minus B is equal to empty. Next, now given again we are having A subset of B, we have to take A union B is equal to B. Now to prove that A union B is equal to B, now if you take let x is equal to A union B. If x is equal to A union B, x will definitely be equal to A, or x will be equal to B, isn't it? Because it will either be in A or it will be in there in B. Then only it is there in A union B. So which implies that x belongs to B or x belongs to B, since A is the subset of B given. Because it's given that A is a subset of B, so definitely x will belong to either B or x will belong to B. So which implies that x belongs to B implies that A union of B is the subset of B. Okay, because we have taken that here it is A is the subset of B. So therefore A union B is the subset of B we got. Also we have B is the subset of A union B. So always this will happen. Therefore A union B is equal to B. Now next, fourth one, to prove that A intersection B is equal to A. Now we are having that A intersection, case 1 we are having here, A intersection B is subset of A. Always we have seen this, isn't it? So therefore let x belongs to A, therefore x will definitely belong to B over here, because it is A is the subset of B. It's given over there. From the first statement we having, since A is the subset of B, if it is belonging to A, it definitely will belong to B. Therefore x belongs to A and x belongs to B implies that x will belong to A intersection B. So A is the subset of A intersection B. Now we have taken that A intersection B is always a subset of A, isn't it? We got that A is a subset of A intersection B. Therefore A intersection B is equal to A. From this statement, and from this statement we can tell that A intersection B is equal to A. Similarly, we can begin with second one and we can prove all the remaining 3 are equivalent. So third one, all the remaining 3 are equivalent. Fourth one, you can make all the 3 equivalent. So you can do any of the process. Now next, question 5. Show that if A is subset of B, then C minus B is the subset of C minus A. Now given A is a subset of B, let x belongs to C minus B, which implies that x belongs to B and x will belong to C and x will not belong to B. So which implies that x belongs to C and x does not belong to A, since A is the subset of B, which is given. So which implies that x belongs to C minus A also. So which implies that C minus B is the subset of C minus A. Because we have that A is the subset of B, that's why we can prove this. Now next, question 6. Assume that P of A is equal to P of B. Show that A is equal to B. Now P of A is equal to P of B means power set of A is equal to power set of B. To show that A is equal to B, so let x belongs to A. Therefore x is the subset of A, the singleton. Whatever we are taking the brackets over here, braces, we can tell this is a set. Whenever it is taking the braces, it's a set, isn't it? So therefore this set is the subset of A, you can write. So since therefore x belongs to power set of A. In the power set of A, you will have this element. Now therefore power x will also belongs to power set of B, since it's given that P of A is equal to P of B is given. Therefore x, this set x is also subset of B. Therefore x belongs to B and therefore A is the subset of B. Similarly B is also subset of A, we can prove. Therefore A is equal to B. Next, going to question 7. Is it true that for any sets A and B, P of A union P of B is equal to P of A union B? We have to justify our answer over here. So now if A is equal to 1 and B is equal to 2, then P of A is equal to, power set of A will definitely be equal to null set and that 1, and power set of B will be equal to null set and 2. So now P of A union of P of B will be equal to this pi empty set 1 union of empty set 2. So we will have pi 1 and 2. Now also A union B is equal to 1 comma 2. Then what is the power set of A union B? You will have pi 1 2 and 1 2 as an in brackets. So therefore now 1 2 belongs to P of A union B. So but 1 2 does not belong to P of A union P of B. You can very clearly see that 1 2 doesn't belong to this set. So therefore P of A union B is different from P of A union of P of B. Now next, going into question 8. Show that for any sets A and B, A is equal to A intersection B union A minus B and A union B minus A is equal to A union B. So now you are having A intersection B, common elements in A and B, union A minus B, only elements of A will be there and whatever are common will cancel out in B, which is equal to A intersection B union of A intersection B dash. We know that this is A minus B is equal to A intersection of B dash. We have already seen this. So therefore A intersection of B union B dash, from distributive law you can write this as A intersection B union of A intersection B dash. So which is equal to B union of B dash is nothing but universal set. So therefore A intersection universal set is equal to A. Now next, here if you see that A union of B minus A is equal to A union of B intersection A dash. Because this can be written, B minus A can be written as B intersection of A dash. Minus is there, we will replace it by intersection, and whenever we are replacing by intersection, we are going to write it as A dash in the last. So therefore that is equal to, if you are taking distributive property, A union B is the intersection of A union A dash. Now what is A union A dash? It's nothing but equal to universal set. So A union B intersection universal set is equal to, whenever you are taking the intersection, whichever is the smallest one will be the answer. Therefore it is equal to A union B. So therefore we got A union B minus A is equal to A union B, hence proved. Next, going into the 9th one. Question 9. Using properties of sets, show that A union A intersection B is equal to A and A intersection A union B is equal to A. Now we know that if A is a subset of B, A union B will be equal to B, because B is the superset, right? So now here A intersection B will be the subset of A. This also you know that because intersection is the common one, so whichever is the smaller one will come here. Intersection you'll get the smaller one, in union you'll get the bigger one, that is superset. So therefore A union of A intersection B is equal to nothing but, you know that A is the bigger set in these two, therefore this is equal to nothing but A, because you're taking the union. That is the answer which we got for the first one. Second one, we know that if A is the subset of B, implies that A intersection B is equal to A, the subset, which is the subset, because intersection means whatever is the smaller one, it will be equal to that. So here A is the subset of A union B. Definitely A union B is the bigger one. So therefore A will definitely be the subset of A union B, or B also can be the subset of A union B. Therefore you are having that A intersection of A union B will be nothing but A, the smaller one. Whenever we are taking intersection, union it is the bigger one, and intersection the smaller one. So therefore A intersection A union B is equal to A is the answer. Next one, show that A intersection B is equal to A intersection C need not imply B is equal to C. Now here you are having, let A be equal to 1 to 3, B be equal to 2 5, C be equal to 2 4. We are taking some example and doing this. Now A intersection B is equal to what here? In A intersection B, what is common? 2 is common in both of them, and this is also common in A intersection C, but B and C are not equivalent sets. So that is what, therefore always it doesn't imply that B is equal to C. So B is not equal to C. For that I have taken the example and done. Okay, going into the next 11th one. What's the 11th one? Let A and B be sets if A intersection X is equal to B intersection X equal to 5, and A union X is equal to B union X for some set X, show that A is equal to B. So now here hints is also given. A is equal to A intersection A union X, B is equal to B intersection B union X, and use distributive property. So now if we take X belongs to A, X will definitely belong to A union X will definitely belong to A union X, because A is the subset of A union X always. Now X will also be equal to B union X, because it is equal to, if it is equal, it's given for us, A union X is equal to B union X. So which implies that X belongs to B or X belongs to X. So now case 1 we have X belongs to B, one case we can take, and the other one we can take that X will belong to capital X, also X will belong to A, and we have to prove that it's belonging to B also. So now how will we do that? So therefore, which implies that X belongs to A intersection X, because X is belonging to X, X will definitely be in A, means both of them intersection also it will be there. So which implies that X will belongs to B intersection X, because A intersection X is equal to B intersection X. It's given to us. So X will belong to B, and X will also belong to capital X. So which implies that X belongs to B also. So therefore in each case X belongs to B. Therefore A is a subset of B. Similarly we can prove that B is a subset of A. Therefore A is equal to B. Now going into the next problem is such that A intersection B, B intersection C, and A intersection C are non-empty sets, and A intersection B intersection C is equal to empty set. So now here what is given, we'll take one example and do over here. So how do we take an example and do? We'll just see. So it's given that A is equal to 1 2, B is equal to 1 3, C is equal to 2 3. So here if we're taking some, in this example, A intersection B is equal to 1, which is not empty. B intersection C is equal to 3. You can see very clearly from these two that it's equal to 3, and from these two you can see very clearly that it's equal to 1. So therefore these two are not empty. A intersection B and B intersection C are not empty. Therefore A intersection C is also not empty, because you can see A intersection C is equal to 2. But you having A intersection B intersection C, there's nothing, 1, which it's also it's equal to empty. How are we taking this? Because here you're having in A intersection B intersection C, you don't have 1 in all the 3, you don't have 2 in all the 3, you don't have 3 in all the 3. So therefore it is empty set. hence proved. Next, going into question 13. In a survey of 600 students in a school, 150 students were found to be taking tea and 225 taking coffee. 100 were taking both tea and coffee. Find how many students were taking neither tea nor coffee. So now here let us consider that number of students drinking tea is equal to n of t is equal to 150. Number of students drinking coffee is equal to n of c, which is equal to 225. So number of students drinking both coffee and tea is equal to n of t intersection c, which is equal to 100. So now here you having that n of t union c is equal to n of t plus n of c minus n of t intersection c. You are having this formula. So which is equal to 150 plus 225 minus 100, which is 275. That is, number of students who take at least one of the two drinks is 275. Therefore, number of students who neither take tea nor coffee is nothing but 600 minus from the total number of students minus who are taking either coffee or tea, which is equal to 270. That is 325. 600 minus 275 is 325. Next, going into question 14. In a group of students, 100 students know Hindi, 50 know English and 25 know both. Each of the students knows either Hindi or English. How many students are there in the group? So let H denote the set of students who know Hindi and E denote the set of students who know English. So n of H is equal to 100, n of E is equal to 50, n of H intersection E is equal to 25 and n of H union E is equal to n of H plus n of E minus n of H intersection E, which is equal to 100 plus 50 minus 25, which is equal to 125. There are 125 students in the group who know at least one of the two languages. So next, going into question 15. In a survey of 60 people, it was found that 25 people read newspaper H, 26 read newspaper T, 26 read newspaper I, 9 read both H and I, 11 read both H and T, 8 read both T and I, 3 read all 3 newspapers. Find the number of people who read at least one of the newspapers. First one, the second one, the number of people who read exactly one newspaper. So here let n of H be equal to number of people who read newspaper H. In the same way we can write n of T is equal to number of people who read newspaper T, I be equal to number of people who read newspaper I. So therefore that is also given to us. N of T is 26, n of I is 26, n of H intersection I is equal to 9, n of H intersection T is equal to 11, n of T intersection I is equal to 8, n of H intersection T intersection I is equal to 3. This is also given to us, is equal to 3. This is also given to us. So number of persons who read at least one of the newspapers is equal to n of H union T union I, which is equal to n of H plus n of T plus n of I minus n of H intersection T minus n of H intersection I minus n of I intersection T plus n of H intersection T intersection I. So just plug in those values whichever are there top of there. You will get 25 plus 26 plus 26 minus 9 minus 11 minus 8 plus 3 is equal to 52. Now the second one, number of people who read exactly one newspaper is equal to n of only H is equal to n of H minus n of H intersection T minus n of H intersection I plus n of H intersection T intersection I, which is equal to 25 minus 11 minus 9 plus 3, which is equal to 8. N of only T is equal to n of T minus n of T intersection H minus T n of T intersection I plus n of H intersection T intersection I, which is equal to 26 minus 11 minus 8 plus 3, which is equal to 10. And n of only I is equal to n of I minus n of I intersection H minus n of I intersection T plus n of T intersection H intersection I, which is equal to 28 minus 8 minus 9 plus 3, which is equal to 12. So therefore number of persons who read exactly one newspaper is equal to n of only H plus n of only T plus n of only I, which is equal to 8 plus 10 plus 12, which is equal to 30. Survey, it was found that 21 people liked product A, 26 people liked product B and 29 liked product C. If 14 people liked products A and B, 12 people liked products C and A, 14 people liked products B and C, and 8 liked all the 3 products, find how many liked products C only. So now here let n of a be set of people who like product A. Number of people who like product A is equal to 21. N of B is set of people who like product B. N of B is equal to 26. N of C is equal to set of people who like product C. That N of C is equal to 29. So now here we are denoting here from the Venn diagram, you can see that A intersection B is this part, that is 6 plus 8 is 14. Then you are having A intersection C is 8 plus 4 is 12. B intersection C is 8 plus 6 which is 14. So A intersection D denote the number of people who like products A and B. N of B intersection C denote the number of people who like products B and C only, and number of people who liked the products C and A only is denoted as N of C intersection A. So all the three products, how many of them liked? 8 of them liked all the three products. So therefore N of A intersection B intersection C, it's denoted as, it's nothing but equal to 8. So now we have to find out, and from the question you can see that how many like product C only. So how many like product C, all the intersection parts whichever are there we have to minus. So we know the number of people who like product C is 29. We have to remove all those intersection parts, that is 4 plus 6 plus 8. If you remove this part which I have covered in yellow, this part, if you remove all this, that is the intersection of all the three, intersection of B intersection C and A intersection C, whatever is there, if you remove that part, we'll get what is the value of number of people who liked product C. So N of C minus 8 plus 4 plus 6, all whichever is there in yellow I have written here. So 29 minus 18 is equal to 11. So number of people who like product C is equal to 11.